In real analysis, we think about differentiation as giving us smaller and smaller and smaller pieces because we're taking the limit as things near the point. And integration for putting everything together, when you think about the Riemann integrals, subdivide, sample, sum, and take the limit, that's about taking a whole domain. The Cauchy representation theorem turns this around quite a bit. So here's the statement of the theorem. This is formula 24 in L4s. And so this tells us how to find the nth derivative of a function. So we would think of that as being an intrinsically local behavior as far as integrating around a circle C. Now, there's a certain amount of detail that one needs to go into. We've got f is presumably analytic, or at least has removable singularities in a big region omega. Being a region, it's open, so around every point there's a disk, and without knowing exactly how that disk is situated with respect to omega, the open disk is in there, but we don't know about the closed disk. So then you have to take a circle C inside that disk to make sure that everything stays within omega. And so that's the C that's in this circle. So this is a small circle around the point that we're interested in. So here we're calling that point Z. This tells us the nth derivative of f at Z, but that can, we use, it doesn't, it's just a name. It's just a name, it doesn't matter. So let me remind you about removable singularities, because that's an important part of what's gone on here, and what will go on. And this is this funny little limit that we've come across before. You know what? It's not funny, and it's not little. It's a serious big limit. So the condition is that the limit for z near a, and remember, z's not going anywhere. It's near a. If you look at the epsilon delta definition, you're seeing that z is not going anywhere. It's near a. And what we're taking the limit of is z minus a times f of z. And this is even if f is not defined at a, because when you're doing the limit for z near a, z can't be equal to a. So f doesn't have to be defined at a for this limit to make sense, or to potentially make sense. And so this limit is 0. That makes z removable. And so that's an important condition. And we're going to put that into action now. So the action comes in the form of Theorem 5 in L4s, which says that if f has removable singularities, then Cauchy's theorem about the integral around a closed curve being 0 still holds. So I'm just going to put this down in words. Cauchy's theorem, which Cauchy's theorem? The one that says all the integrals are 0. Yeah. So Cauchy's theorem still holds if the function has removable singularities. And so this seems like an almost silly thing, but obviously I'm making a big deal of it. It is not. Okay, and I forgot the theorem numbers, Theorem 5. So that's Theorem 5 in L4s. Now, this is, we can put this into action in a couple of ways. First of all, this is almost like there's no such thing as a removable singularity. So this is L4's Theorem 7. And Theorem 7 says that if f is analytic in a punctured domain, so what I'm going to do is I'm going to call the puncture point A and the domain omega, so that's set theoretic difference, so that's omega except for the point A. So if f is analytic in that punctured plane, A is removable, so that's the limit that we've been talking about. A is removable if and only if F extends to A. Well, if A is removable and F extends there, then it's not a singularity at all. Why do we need this? I'm going to show you why we need this. So, and this is done by using the Cauchy representation formula. So the integral is valid, and I'll write down what the integral is. It's 1 over 2 pi I. Someone ought to invent a symbol for that, like some Greek letter that isn't used for anything else, which is kind of hard to come by. But, this is the 1 over 2 pi I. That's worth its own name because that comes up so much. Anyway, we're going to take the integral over some appropriate closed curve of a fraction f of zeta d zeta. So the variable along the curve is zeta, and on the bottom is zeta minus a. So there's the Cauchy representation. Now, what do we need this for? Well, it's pretty interesting to see what we need this for, because it's going to be something that's obvious. But what we're going to do is we're going to make a new function, capital F of z, and that's going to be a fraction, and the bottom's going to be z minus a. So the a is some kind of point of interest. It is obviously a singularity for big F. I'll write it. I'll show you the whole thing in a second. The top is the difference between f of z and f of a. So this is one way of writing the difference quotient that goes into taking the derivative. And in fact, we know under the right circumstances, which is basically always, if z is near a and we take that limit, then the limit is f prime of a, little f prime. We've got a big F and a little f. So I'm going to just remind you that that's what the limit is. So here we're inventing a function that's clearly not defined at a. And on the other hand, it's clearly a removable singularity. If we multiply this by z minus a, all the problems disappear. And so this is a removable singularity. So f has a removable singularity, and so it extends, just like we talked about with Theorem 7, and we're going to repeat that. Only what we're going to do is define a new function, f1 of z, and f1 of z has a pretty simple definition. It's big F, so that's going to be like the derivative. If z is not a, big F is not defined when z is a, and we're just going to have little f prime of a if z is equal to a. So this is the extended function f1, and that's analytic. That's what that previous theorem said. So now what we're going to do is rewrite what we had here. And so when I rewrite it, it's going to look like this. And this is going to be kind of like, almost but not quite, really reminiscent of, as useful as the tangent line approximation that is so important in ordinary single value calculus. So what I'm going to write is this, that f of z, that's little f of z, is equal to f of a plus z minus a. I've just done some very simple algebra here, times f1 of z. So that's based on algebra with the definition of f1, and it's here in red. And that looks like, that starts off the same as the tangent line approximation. The only difference is we're using f1, which is closely related to the derivative, but it may not exactly be the derivative. So there we go. We're going to do that. And then we're going to repeat this process, and repeat this process, and repeat this process, and we're going to come up with a short sequence of functions. This is a finite sequence, so it's a short set of functions where we're going to have f sub n minus 1, I guess. Sorry. F sub n minus 1 of z is f sub n minus 1 of a plus z minus a times f sub n of z. So we've actually I'm repeating Alfors's mistake. We should have called f sub 0 the function f. So this happens if you perform this process to f1, then you get f2. If you perform this to f2, you get f3, so forth and so on. So we get all these functions, all these tangent line approximations, but these are going further and further and further down into the depths of the function and all of its derivatives. And so when you put these all together, you get an expression like this, f of z. I'm just going to keep adding these together, is, well, we're going to start off with f of a, this is everything's happening at a, plus z minus a times f sub 1 of a, that's almost a tangent line approximation, plus z minus a quantity squared times f sub 2 of a. You might have seen this in Calculus 2 or Calculus 3 when you're talking about Hessians. And we keep going, and we're going to do n terms like this. So we're going to end up with z minus a to the n f sub n of a. So the only variable here is z. Everything else is constant. Everything else, f of a is a constant, f prime of a is a constant, and so forth and so on. So we get this. And now we get to something that's going to look familiar, but with a little bit of a difference. We've been flirting all along with the tangent line approximation. And if you keep flirting forever, that's no comment on your love life. If you keep flirting forever, you will come up with the Taylor series for f, which presumably you're familiar with. But we're not going to flirt forever. So what we're going to do is cut the Taylor series off, but now we have a statement about how much we've cut off. And so what we're ending up with here is, well, you start taking derivatives of this right here and plug in z equals a, and every time you do that, only one term remains. You get the derivative, that'll give you a constant term. When you plug in z equals a, everything else turns to 0. So what you end up with is the common expression for the Taylor series, but it's going to be cut short. So we're going to have f of a plus f prime of a over 1 factorial. You need to see the pattern, so you need that 1 factorial. Even though it's equal to 1, there it is. So that's times z minus a. And we're going to keep going in the same old Taylor series way. The next term is a fraction. The top is nth derivative of f at a. And the bottom is n minus 1 factorial. If I said nth term, I meant n minus first derivative. But now you'll have z minus a to the n minus 1, and instead of continuing that like you would if you were doing a Taylor series, what you end up doing is you just kind of punt and say, well, plus z minus a to the n times f sub n of z. So it's a lot of ink under the bridge there. Okay, so the one thing that happens, and Alfors doesn't. This is just algebra. If you take this Cauchy representation and apply it through here and do something, you can get an integral expression for f sub n, which is a very useful thing. So I'm going to write that down, and then we're going to call it good. So f sub n of z is now, what are we going to call this thing? 1 over 2 pi I. It's a very important constant. It's almost as important as pi itself. Integral over a circle C, that's the same circle that we were talking about before. So as far as doing the parentheses first, there it is. And it's going to be a fraction. The top is, oh, you're going to be tired of saying this? No, this is amazing. F of zeta d zeta. So zeta is the variable along the circle. And on the bottom, we have two factors. One is zeta minus a to the n. So a was our removable singularity, and we're seeing how far that is from zeta, and then zeta minus z, which is where we want to evaluate f sub n. So this integration formula changes, which you think would be doing global behavior, actually tells you how to handle the local behavior in a very precise way. And so there are a lot of consequences of this, but this is the start right here. So remove your singularities and enjoy life.